Our example problem here, we have an ideal gas initially at 300 Kelvin undergoes an isobaric expansion at 2.5 kilopascals. If the volume increases from 1 cubic meter to 3 cubic meters, and if 12.5 kilojoules of energy are transferred to the gas by heat, what are the change in internal energy of the gas and the final temperature of the gas? Okay, as we solve problems like this, not only do we want to identify what all the numbers represent, but we also want to identify what type of process we have. So this is isobaric. I didn't necessarily need to underline the expansion part. It's the isobaric that's important. Constant pressure, because that will determine some of the equations we can use. If we look at the table in the test notes, the line that has constant pressure on it has, for example, work is negative P delta V. That will be an option. Q is N Cp delta T. So there's a variety of equations that can technically apply. I'm going to go ahead and write down what we know as well. So we're initially at 300 Kelvin. This expansion is happening at a pressure of 2.5 kilopascals. It's constant, so that's why I'm not putting a subscript on it. It's not changing. We have our volume. Initial is going to be 1 cubic meter. Our final volume is going to be 3 meters cubed. Now this 12.5 kilojoules of energy transferred to the gas means it's going to be positive, because we're using the convention that energy going in is positive, energy out is negative. Now it tells us this energy is transferred to the gas by heat. That means this is Q. So we're trying to find the change in internal energy, which is also delta E thermal. And we want to find the final temperature of the gas. So if we jump over to the test notes, here's our test notes. Constant pressure, well, we have this relationship between temperature and volume that's actually going to help with finding the final temperature. So if we come back, T initial over V initial equals T final over V final. We know initially we have 300 Kelvin and 1 meter cubed. Well, our volume's tripling, which means the temperature also has to triple, which if we just cross multiply, we see that as well. The final temperature will be 900 Kelvin. So we've answered the second part first, and that's totally fine. We want also to find the change in internal energy. And when we come back to this table, the row that has constant pressure on it does not have a specific equation for change in internal energy. So we want to think about the first law of thermodynamics and or this equation for the change in internal energy as NCV delta T. That's always true. The first law of thermodynamics must always be satisfied, and then this is always the change in internal energy. The CV, though, depends upon whether we have a monatomic or diatomic gas. Coming back, all we know is we have an ideal gas. We don't know if it's monatomic or diatomic, so we don't want to use an equation that has CP or CV in it. So let's look at this one. The first law of thermodynamics tells us that the change in thermal energy must equal Q plus work. So heat plus work. This problem gave us the heat. So if we can find the work, which we easily can, this was one of the equations that was specifically listed for isobaric, then we can find the thermal energy this way. All right, so we have 12.5 kilojoules for the heat. The work is negative P, which is 2.5 kilopascals, times delta V. Delta anything is always the final value minus the initial. So 3 minus 1, both of those are in meters cubed. So Q, 12.5 kilojoules. I have 2.5 kilopascals times 2 meters cubed. That gives me 5 kilojoules. The pascal times the meter cubed is a joule. So I can technically leave both of these in kilojoules, and I end up with 7.5 kilojoules is the change in thermal energy, which is also the change in internal energy. So the temperature went up, as we've already seen. Delta E thermal is positive because the temperature went up.